This is Geology 100 Natural Disasters. My name is Dr. Scott Nowicki, and today's topic is seismically and volcanically triggered events, landslides, laharas, and tsunamis. We are going to investigate both what causes these events and what they look like when they actually occur. The sign that you see here is a tsunami hazard zone sign. If you have ever lived along the coast in California, Oregon, or Washington, you may have seen these signs. They are specifically posted in locations that could be affected by a tsunami should it happen. And it turns out the west coast of the United States is a place where tsunamis can certainly occur. To begin with, let's define what each of these different events are. A landslide is the movement of surface materials downhill under the force of gravity, but it can be triggered by a number of different types of events, such as an earthquake or volcanic earthquake, but it could also be induced by a big storm if runoff from roofs gets dumped down into the soil. A lahar is fairly specific. It is the mass movement, effectively a landslide or a mudslide, of wet, muddy debris downhill under the force of gravity, specifically triggered by a volcanic eruption, volcanic outgassing, or high heat flow on the slopes of a volcano. And then finally, there are tsunamis. Tsunamis are seismically, volcanically, or landslide-induced water waves. They can also be called tidal waves. They tend to occur in the ocean, but in some very large lakes they can occur as well. These can be caused by any number of events. Big earthquakes, large volcanic eruptions, undersea eruptions, and of course undersea landslides, or landslides that go from the land down into the water. We're going to start with landslides, and here is an example of a landslide that occurred not too long ago. This is the Cedar Canyon Road in Utah. If you've ever driven from Cedar City up the mountain towards Bryan Head, this is that road, and this was a number of years ago when a big storm occurred in the spring and increased the fluidity of the soil. The entire thing became unstable and it slid straight downhill. So here's an image showing where that road used to cut straight across the center of the image. It all slid down into the canyon. Landslides are any number of types of movements of soil, rock, debris, loose material, even solid material that slides downhill. Type A is a rotational landslide. It starts off at a high angle, and that uppermost surface actually slides down and the entire thing rotates in order to allow the toe to flow out onto the surface. Whereas a translational landslide, there is no rotation, it's just a sliding straight down the slope. A block slide looks somewhat similar to a translational landslide. A block slide is, again, these blocks moving as a coherent mass but downslope. A rockfall is rocks that come off of the wall or come off of these high slopes and slide down onto the road. A topple is the type of thing that you might see in a canyon type topography. Over time, erosion and weathering occur and they loosen up these large blocks of material, and then as these blocks topple over, there's your rock topple. A debris flow is what we're going to see quite a few more images of, and as you watch the videos that I've posted, you'll see examples of debris flows. They are fluidized soils and debris that flow almost as a liquid downhill. A debris avalanche is somewhat similar to a debris flow, but the debris avalanche works its way straight downhill, very similar to a rockfall. The earth flow is a fluidized movement of soil. Creep is a slow scale or slowly moving version of these landslides. Finally, a lateral spread down here is where typically a stream channel carves out void space, and that allows soil and rocks to actually laterally move into that void space. So a number of different landslide types. Here's a simple model of the morphology of an earth flow. There tends to be a crown, an uppermost part, where there is the head scarp or the main scarp, and then the head of the flow. So in this case it is a rotational landslide. So originally this surface was up with the rest of this surface here, and as it got loaded with mass, or as that main scarp was lubricated, this entire thing rotated through, allowing that material to come and flow out of the rotational portion. So there are these scarps that tend to be parallel with the main scarp. There are transverse cracks. There are hummocky terrain, and then there's the toe of the landslide itself. These sets of characteristics don't have to occur in every type of earth flow, but they are fairly common. I'm going to show you an example that occurred in Portland, Oregon. It is actually a slow-moving or a creeping landslide. This area is an apartment complex that was built a number of years ago on an ancient active landslide, and as a function of that, it is sliding downhill. So here are these parallel fractures, and this is pretty close to the headscarp, showing a foot or two of relief at each of these little fractures that allows this landslide to continue to rotate and move downhill. So these scarps really indicate the fact that this soil surface that used to be up here is sliding downhill as a somewhat coherent mass. And that is often a obvious characteristic of these earth flows, is that that uppermost headscarp and the head of the flow stays as a somewhat coherent mass as it slides downhill. There are both natural and human causes to landslides. These natural causes are what you would expect. Tectonic or volcanic uplift, changes to the landscape that are creating an unstable surface. It could be glacial rebound. Over long periods of time, as the morphology changes, it becomes unstable. Erosion of the slope toe or erosion on the lateral margins can destabilize a landslide as well. As water is flowing through the subsurface, it's removing material, so that would be solution or dissolution or piping. There could be deposition or loading at the slope or at the crest. Usually vegetation is a stabilizing effect. As vegetation is removed, it could destabilize that slope. Thawing of permafrost can often induce landslides. Freeze and thaw weathering can induce small-scale changes that over long periods of time can really cause large-scale movement, and then shrink and swell weathering. As soil becomes wet and then dries back out, it effectively loosens these materials. Now the human causes are often very parallel or very similar to these natural causes. Excavation of the slope or its toe is one common way that these landslides start to occur. As you remove material from the bottom, there's not enough mass holding the landslide up, so it will actually start to move. Or load the top of it, which will then push down on the head and push down on the headscarp. Drawdown of reservoirs, changing the amount of water in the subsurface. Deforestation, again removal of vegetation. Irrigation, which is just increasing the amount of water in the soil. Mining or subterranean removal of mass. Artificial vibration due to roadways or construction or mining. And then finally, water leakage from utilities. And when we see these landslides occurring in residential areas, that's typically the number one cause. So the way to cause a landslide is to load the head with mass, to reduce the toe material in terms of mass so that there is less holding the slide up, or to lubricate the mass itself. To load the head means to build a house at the top of a slope, or to reduce the toe might be to build a roadway down here and cut away at the base of that slope, or lubricating the mass, floods or large rainstorms. These things are pretty common. The second type of event that we're going to look at are lahars, and these are these debris flows or mud flows that are caused by a volcanic eruption, volcanic emission, or volcanic earthquake. And here is our image of volcanic hazards, and lahars are these mud or debris flows that run downhill for the most part through drainage channels, through stream beds, through arroyos, but it's all entirely induced by a volcanic event. Mount St. Helens is a really good example of where we saw some amazing lahars. So here's an image of the mountain itself, and what we're looking at, this dark area, is actually the pyroclastic flow. But around Mount St. Helens itself, there are lots of areas that had these mud flows. So the brown areas we were looking at from the north, looking at Mount St. Helens. So here is that darker pyroclastic flow. But all along the southern, eastern, and western side were these mud flows that headed downhill once the eruption occurred in 1980. And then there was a debris avalanche that made its way down to the Toutle River. And finally, these mud flows continued for tens of miles away from Mount St. Helens. So these are normally occurring on steep slopes anytime that a volcanic eruption occurs. The debris flow, or the lahars, pick up everything in its path and carry it downhill. It could be trees, it could be dirt, it could be rocks. Around the world, lahars are one of the more dangerous volcanic hazards because they can travel such long distances. Mount Rainier has the distinction of having an extremely high potential for lahars and a large number of people that are actually living within the lahar zone. Geologists have mapped these lahar deposits from previous volcanic events, and as Mount Rainier either erupts or degasses, volcanic earthquakes that occur, this will cause a lot of these debris flows to start. So each of these zones in these different colors, purple, yellow, orange, are all these lahars that have occurred in the past. To project into the future, the likelihood that lahars will occur again from Mount Rainier and run downhill, winding up in these towns outside of Tacoma, are fairly likely. We are seeing recurrence interval on the orders of hundreds of years, suggesting that these things could occur at any point. There's enough glacial ice, there's enough water, there's enough mud and loose materials on Mount Rainier that it could at any point give way. So what you need to make a lahar is, first of all, sediment and debris on a slope. It could be pyroclastic materials, could be ash, glacial sediments, gravel, trees, soil. All of these materials are readily available on most volcanoes. The second thing you need is water, and water is typically available in these glacial ice packs. Could be in snowpack, could be in hydrothermal water within the system itself. Of course, there's rain throughout the Cascades, or could even be mountain lakes, standing water on the surface. And then third, you need a trigger. If magma is moving towards the surface, it's able to dump a lot of heat out. That could melt the bottom of these glaciers and turn it into water that is available to run downhill. The second is volcanic eruption. Mount St Helens in 1980 was a massive eruption. Volcanic outgassing can also cause these, and then earthquakes. So these things are pretty common. When we look at all of these Cascade volcanoes, as well as volcanoes around the world, all of these pieces are in place, and really it's these triggers that kick off these lahars on a regular basis that cause huge amounts of damage and lots of loss of life. The third type of event that we're going to describe are these tsunamis, massive waves of water that are generated from an undersea event. It could be a underwater landslide, it could be a volcanic eruption, or it could be movement along a fault. Here is a graphic showing the effects of the 2004 Indian Ocean earthquake. It was a magnitude 9.0 earthquake that occurred just offshore of Sumatra, but it was a large amount of movement that occurred within that fault, pushing a lot of water and generating this massive wave that shot through the Indian Ocean. Starting from Sumatra, it radiated out in all directions, and of course the closer the people were to the epicenter of this earthquake, the bigger the effect of the tsunami. What we saw in the 2004 tsunami was really a rise of the ocean and a large wall of water that went inland. The shoreline was completely inundated by a large wave, and the wave varied in height. It was many meters in some locations, and it was only a meter in other locations. Tsunamis travel very quickly on the open ocean, but their power comes from actually hitting the coast and ramping that wave up, so that these seismic events that occur out in the ocean hundreds of miles away from shore, and a tsunami could pass and you wouldn't even notice. It would be a gentle rise in the water height, and it would continue on. But as it runs towards shore, these waves build up height and energy as they come crashing into the shore. If we were to look at the United States and places where we have been affected by tsunamis, it turns out it's primarily in the Pacific Ocean. This is because there is a lot more tectonic activity in the Pacific Ocean, in this Pacific Ring of Fire. But in 1964, one of the biggest earthquakes generated this tsunami that affected the entire west coast of the United States, as well as coast all along in Alaska. Previous earthquakes There were a number of tsunamis that actually are recorded as well. We have that 1700 year 1700 Cascadia earthquake and tsunami that affected Oregon, Washington, and Northern California. So there is a lot of evidence of tsunamis that have occurred in the past that devastated the West Coast. As we look into the future, this of course is also the location where the potential is the highest.